Oh, it will follow me, is it? I will anyway just sit down here, so I won't I won't move. Oh, okay. Interesting. Hello. Working, right? Yeah. Yeah, yeah, no, no issues, no issues. I think after 45 minutes to, I think it was around 10:45 is some, you know, so 11 o'clock. Yeah. Uh, where is? I think we have the schedule on the meetup page. Where is the meetup page? We can keep it right now because they can ask questions in between. Yeah. So I think here we have on mobile you don't get schedule, is it? Yeah, because on computer you get. Yeah. Ah, this is the one. So yeah. 11. I mean that was like tentative, but it will be around. So I will have like generally what I'm trying to do is four sessions of 45 to 50 minutes each. So bundle of papers or a small diary? Yeah, yeah. A very, very small notebook should be good enough. I mean, just a few pages for me too. Even if you have something like a story card, that should be good enough. I mean, I just want to. Okay. Yeah, because I forgot my diary at the hotel. Hello, hello, hello. Yeah, we can. Okay.
Okay, thank you everyone for coming on a Saturday morning, but most importantly, thanks to Unmesh for braving a lot of challenges, failures, outages, etc., etc., and making it from
Yeah,
Pune
different kind of failures, but
yeah, for making it from
but
Pune to Bangalore. So
yeah,
on Thursday when he was at the airport at about 3:45, suddenly he called and said the flight is cancelled. And I said, is it only your ticket that's cancelled or the entire flight that's cancelled? He said, entire flight is cancelled. I'm like, oh. I'm like, okay, well, you have to book a ticket now. And so there were two flight tickets remaining, and I was racing against time to get one ticket. But he's here, and
yeah,
hopefully he'll get back tomorrow.
yeah.
Because
Hopefully, because I just see a news that multiple Indigo flights are grounded because of again some failure somewhere in software upgrade. It's crazy, you know.
so yeah, so we thought
But
we should start the workshop with this example. But
yeah,
anyway, so thanks to Unmesh for being here. Thanks to E6 Data for hosting this workshop, and of course, most importantly, thanks to all of you for showing up. And like I told Unmesh, I feel like a Bollywood movie producer bringing him here. But yeah, over to you, Unmesh.
cool. Thanks, thanks. Uh, cool. So, I mean, the title of the workshop is physics. What is the title? Understanding the physics of distributed systems and outages and stuff like that. But essentially, what we'll be looking at is when we call something as a distributed system, and that includes things like Amazon S3, message brokers like Kafka, or distributed databases, or even orchestrators like Kubernetes. Why do they exist in the first place? And why are they designed the way they are? And outages, when we say outages, why do they happen in the first place? And how some of these designs are done to mask those outages from end users. So the repository that I have shared, it has 5 sections, um, and each section is so first 2 sections are just few scripts that we will execute on a Docker container. I mean, just to see, learn few things about how saturation looks like, and when we need multiple components to uh, work around that saturation. And then from section 3, 4, 5, we have section 3 and 4 are essentially Java projects. Section 3 is an example implementation of a technique called erasure coding, which is used by object stores like Amazon S3, or if you are aware of open source alternative to S3 called Minayo. It uses that kind of a technique. The fourth is a very miniature implementation of Apache Kafka. So it's like a bonsai, a small Kafka built from scratch. And what we'll do is some assignments to complete some of the code snippets to understand how it works. And the fifth is a separate Go project, which is a miniature Kubernetes implementation. And this is the main branch, and each has so each folder has a README and a lab or a exercises.md, which talks about what we need to do. So we'll be mostly like you can consider each of that section is like 1 45-minute section that we'll do, and then we'll take a break after every 45 to 50 minutes. And I do have a presentation as well that I will use to guide some of the discussion mostly. Okay, I removed the word outages from here because I experienced too many of them in last few days. But we'll start with some of the foundations, and any typical architecture for last 20-ish years. Yeah. Oh, not audible. Hello. Oh, ma'am. Okay. Okay. No. Okay. Yeah. Yes. Hello. You can hear me now. Okay. So we will try to understand why distributed systems exist in the first place, and we'll take help of a typical architecture that we all are used to in the web era. So this is standard 3-tier architecture, right? So we have data that is stored separately in a database, and application logic that we'll write in our general purpose programming languages like Java, Golang, and any other, which is mostly exposing some kind of APIs, mostly web APIs, and then you have a very lightweight front end or a mobile app which uses those APIs. And one of the key characteristics of this architecture is that the stateful part, the part of the architecture which deals with data, is separated out from part of the architecture which handles user requests and has business logic. By the way, you can ask questions in between because I mean, just to be frank, I am also learning a lot of these things. So I learned by building my own miniature versions of it, and the reason for that was because I did not understand a lot of books that I read. So feel free to ask questions if you don't understand anything. Maybe I also not have understood, and maybe because of that I'm not explaining well. So we'll discuss and then figure out together what we don't understand. So just feel free to ask. We'll keep it more conversational. Now, the key characteristics, as I said, is that we separate out data from state from stateless part of our architecture, and it helps very well with web kind of architectures, with the assumption that if the ratio of your read to write requests is very skewed, like you have a lot of read requests and very few write requests, then you can possibly cache your data away from the component that handles your state and just use that to send it to your users. And when we say scaling, mostly we say that our system is horizontally scalable, and when we say that, we a lot of times talk mostly about this app layer, where you can add more instances as user load goes up. Now, all this works under a very basic assumption, a very fundamental assumption that the part that's handling our data, which is mostly our database, and that's a very standard database like a Postgres or Oracle or SQL Server. However we scale this app server part, that single database is able to handle all the load, and that's the assumption we typically have. So if you look at the production setups for this kind of architectures, you will see that your database configuration, the hardware configuration, will be pretty high. I mean, it will have a lot of RAM, a lot of disk, and a lot of CPUs. And as compared to that, your stateless piece will have lesser number of CPUs and memory. And essentially you do that to make sure that even if you scale this piece horizontally, you have enough room to handle that load on your database. And this has been working well, right? Even today, when we build microservices, your standard data storage for any microservice is a Postgres or a MySQL or Oracle kind of a database, right? Very few times we go for distributed databases. What we will be talking about is about distributed databases, but we'll see why. Now, that assumption we had here that our database and whatever capacity we allocate for that database is able to handle all of the load when we horizontally scale our stateless piece. When that breaks, and when that breaks is, let's say, every request that you assume that won't go to your database starts going to your database. Maybe your reads and writes that you assumed that the percentage of reads will be 80%, let's say, and only 20% will be writes. That goes down, maybe because of some marketing campaign that asks users to enter their data that needs to be stored, and you suddenly get like million hits to store data. And when that starts, that assumption starts to break, essentially you see the symptoms, and the first symptom you see is that the user requests that are going to your application, they will start experiencing higher latency, or maybe timeouts that those won't be served. Now, whenever that kind of situation happens, right, any kind of outage or any kind of issue like your request getting timeout and stuff like that, whether we are using a database or any other product or any other software, by the way, that's written all around the world, issues happen only because of these four physical components, because the hardware architecture where your software runs, it has not changed in last so many years, and in foreseeable future it's not going to change. So you have a CPU where you process stuff, and then that CPU accesses dynamic memory or random access memory, which is very fast, but it's limited in size. And then for communicating between any two computers, you need network. And then there is a component called disks, which is either a solid state drive or hard drive. And any time you want to persist any data and give durability guarantee that even after a server restart, you need to get that data back, you store that on the disk. So these four physical components, and stressing on the word physical. They are the reason for any outage that happens in the world. And when we talk about physical components, there are physical limits to those components, right? I mean, starting from how fast how fast CPU you can build, because you know that CPUs have reached a limit of clock frequency, and beyond that they heat up a lot, right? So there is a limit to that. There is a limit to how much random access memory you can have on your server. Like if you have a really huge machines that you buy, maybe terabyte, but it will never be petabytes. There is a limit to how much data you can transfer over a network. So currently we are connected to this Wi-Fi, which is a 5G Wi-Fi. So maybe what we are getting right now is say 100 Mbps bandwidth, right? So we will be able to transmit 100 Mbps. Same way when you have your servers in your data center, they are connected to network cables, and you need to decide how much network capacity you allocate. And then disks, which is the most interesting piece, because it is the slowest. Storing data and reading data from disk is one of the most tricky things, because it's very slow. And you'll see that starting from operating system to any other architecture, any other storage architecture that's built, like databases or message brokers or anything else, it does some clever tricks essentially to avoid accessing disks for serving user requests, because as Roy Fielding has famously said, Roy Fielding, person who invented REST and HTTP. So the best way to optimize anything, to not use it. I mean, he said best way to optimize network is to not use it. If you want to optimize disk, the best way is not use it. Serve your requests from somewhere else. So now, what does it mean that these physical limits, I mean, what happens when these physical limits, you start hitting these physical limits, and just to talk about some examples. Let's say you have a 1 Gbps network connected to your server, and GB, again there is a fine print there that when you talk about network bandwidths, the B there is a small b, that means bits per second. So even if you have like 1 gigabits that you can transmit over that network in a second, what that means is it translates to 125 MB of data over that network. And when you map it to user requests that you are trying to serve, and they are combined like read and write, because all the data will go through the same network. And let's say you have very small requests, like very small amount of data you are transmitting over that for per user request. And now this depends again on the nature of your application, because if you are let's say writing a video streaming app, then files will be large files that you will transmit. But even if let's say we have like very small 1 kilobyte, and 1 kilobyte is let's say a single key value, right? Single key value like a name and some description. It will be 1 kilobyte of data. Then on that particular network, you will be able to serve only 125,000 of such requests, right? So that's the maximum capacity of that network. Beyond that, we'll see what happens beyond that. But essentially, your requests will be queued somewhere, right? They won't be served. And disks, I said, are the trickiest because they are the slowest. And even the bandwidth, they do have bandwidth as well, because anytime you transfer data from one physical component to other physical component, it needs to be attached to some transport layer that transfers that data. And disks also have are attached to the message bus on your motherboard, and depending on the kind of technology used for that data transfer, it decides how much data you can transfer in one go, or per second, and that's the bandwidth for that. So for example, the latest tech is non-volatile memory express bus, and if you have your solid state drives attached to that kind of a bus, let's say you get transfer speeds of 2 gigabytes per second, best in class hardware if you have. But again, that's expensive. So if you have lots and lots of data and you want to don't spend a lot of money, and you go with, say, mechanical drives or standard hard disks, then you see that the transfer bandwidth or transfer speed in layman terms is 500 MB per second. And how that matters is that, and that matters more for, have you heard terms like OLTP and OLAP? I'm sure. So OLTP is online transaction processing system, and again, the key characteristic there is because you are serving user requests, you are interested in very specific data. So even if you have like a 1 terabyte data lying around on a disk, maybe you are interested in only 10 kilobyte data from that 1 terabyte. So most of the efforts that go in for OLTP data access is to quickly figure out where that data is located on the disk, on the file, and just read that much, like 10 kilobyte, and return that. And OLAP, where it's analytical processing, mostly big data systems, where you are not interested in like serving an individual query and return like a small data for that user, but you are interested in like analyze data for, let's say, last 3 months or last 6 months. And what that means is that for processing that data, you need to access let's say petabyte of data. I mean, depending again on the kind of, but and when you need to access that kind of data, you see that this transfer bandwidths and the technology used and the hardware used, it starts to impact your decisions of how to write your software. So if you look at the numbers, like 1 terabyte data, and you need to access, let's say, all of that for processing, on a 2 Gbps NVMe SSD, it will take 500 seconds. I mean, just to transfer that data on the over the bus, and after that you will process and again store it somewhere. That's apart. But if you have slow disks, like mechanical hard disk, then that time goes ridiculously high, right? Like 2000 seconds, and for 10 terabyte data, it will be like 5 hours just to load that data. And that is one of the reasons why big data systems exist, and they are designed the way they are. So what they do is, instead of keeping data on one hard drive, you split it across, say, 100 hard drives, and then on each hard drive you pick only specific smaller amount of data, and you also process it on a different server. So this is what we looked at is the limit or limiting numbers of these physical components, and similarly you will have numbers for, depending on again the nature of your code or nature of your application. There will be limiting numbers for CPU and memory as well. Like what causes, let's say if something causes 100% CPU usage for all the requests, then it's an issue. Oops, sorry. Now, to know the impact of this what is called as saturation. So the numbers that we looked at, when those numbers are reached, what we say is that your physical device has reached its capacity and it's saturated. So translated into, you will see utilization of that device going to 100%, right? And if we need to understand the impact of anything that's reaching saturation on the requests that you're serving, there is a very nice law in the queuing system. I mean, if you have heard of queuing systems or studied them, called as Little's law. And what Little's law allows you to compute is if you know how many requests you are getting per second, and either user requests or requests to these physical components, like how many disk accesses, like IOPS, you might have heard, and you know you measure the service time, the time it takes to serve that particular request, then you essentially know the impact on queuing, like how many requests will be queued, or how many requests will be in the system. And it allows you to, and we'll do some exercise on this, and it allows you to observe some of your system components like disk, and then using this law you can compute at what point your disk might reach saturation, or your network might reach saturation, and then you decide, let's say you probably need to split into 10 disks or 100 disks, right? So it helps you with capacity planning. Again, I haven't seen, I mean, this is very useful thinking tool, I would say, but is anyone involved in doing capacity planning in your organization? Because you, so do you use Little's law, or you go by rule of thumb? Guesstimates, right? Yeah, so most of it.
Over the course of the practice, we came up with something similar. I just didn't know it was called.
Right. Yeah, it's very obvious, because you do math, like if for this many user requests, this is reaching say 80%, with this much data getting transmitted, maybe I need double the capacity. I mean, you can do like that. Right. So this assumes average over time. Right. So it, right. Yeah. So we'll see. So why it's good to be aware of Little's law, essentially, is even if you don't use it in practice, there are these standard throughput and latency curves that are good to be aware of. And the latency curve is, so on the x-axis, let's say you are getting number of requests per second, and as it goes on, as you get more and more of requests and your physical devices start saturating, you see this kind of a curve where you see that the curve where it's sharply going up, and at that point you will start experiencing huge latency delays, and corresponding throughput curve will be as you are within the capacity, as number of requests go increasing, your software and hardware combined will be able to serve all those requests. But as you reach saturation, your throughput will drop beyond that point, and and any system, when we say that the system is scalable, we design it in such a way that as you add more capacity to your system always remains on the left side of that red line. So it never reaches a point where it saturates something and then your throughput starts to drop and latency starts to grow up. Right. And as I said, you won't typically use these kind of I mean you will go by the observations that you have in your production environments, and it's generally a rule of thumb or a back of the envelope calculations that you do, and you will allocate more and more capacity based on that. But it's good to be aware of this. And what we'll do now is we see how this looks in practice. So there is a small exercise that we'll do, and what we'll do is we have a script that just writes a file or writes to a file periodically for some amount of time, and there are observability tools that are typically available on any operating system to observe all these 4 physical components: so disk, network, CPU, and memory. So we'll use one of that called IOStat, and IOStat is used for observing your disks, how much utilization, under what utilization the disk is, and what is the wait time for write requests, what is the size of your write request, and stuff like that. And we'll just see how that looks like, and maybe try to predict when it will reach 100% saturation. So see if you have pulled this image and tagged this image as a perf lab. Okay, I'll just exit from here. Is that visible? But even if it's not, I mean, you can just follow the README. So if you have this disk image, what we'll do is we'll start a container. This is a standard Ubuntu container with all the observability tools in there. Yeah, and we'll just run this. So let's say you go to this section 1. And we run it here, and then in another terminal what you can do is you just attach to this particular Docker container. So you go into this Docker container where we will be running. Yeah. You zoom it here. Command plus should do it, huh? Okay. I will do it here as well. So everyone has the image, or you are still? So if you run this, and in another container you just run this iostat x1. So every 1 second it will print the. So what you will, I think it's not very visible thanks to Linux, but you will see things like percent utilization, and this is the number. Like I think it's closer to 50. Then there are things like reads per second and kilobytes of reads per second versus writes per second and kilobytes of writes per second. Then how many requests, what is the time the read requests are waiting versus what is the write await. And then there is average queue size, that is how many requests are waiting to be served from the disk. So in the other terminal, you attach to that container, that where we are running the disk load. And this is a very standard. I mean, we are using a tool called DD to just copy a file. So 4K is the amount of data it writes in one go, in one write operation, and 60 is just a 60-second it will keep on writing. No, I mean you can call it anything. So it's just a name, some name that it has random bytes that are written. So there is nothing in there. It's just the name of the output file that it will. So if you look at this disk load, it is just using the standard disk duplicator. So this can very well be replaced by maybe a simple Java or Golang or whatever program you write. Just in a tight loop you keep on writing to the file and observe these numbers. The interesting piece, I mean, if you have completed that, the interesting thing, if you look at this lab.md file in this workspace, the numbers that you see here, right? This read request per second, write request per second, read await, write await, average queue size, and percentage utilization. They can be derived from Little's law that we just saw, and so your lambda is total reads and writes per second, requests per second. Wait time is write await, and then total requests that are in your system, including the ones which are queued, is essentially lambda into W. So the numbers that you see in IOStat should match this calculation. And then with some of the, I mean, I won't maybe go through all of that, it's already 11. But you can then substitute when this disk is will reach saturation. So if you see this third assignment where what is the maximum IOPS this disk can support if you are doing reads or writes, and that comes out to be 17,000, around 17.5 thousand. And then if your application is going to need, let's say, depending on the load on that application, let's say 50,000 IOPS that you need, 50,000 writes and reads per second, then obviously this single disk is won't be able to serve that. So you need to then split that into 3 disks, and that's like the rough calculation that you can do for doing capacity planning. So this lab has some example calculations that you can go through. I mean, one of the things why I have this code base is this can give you a good test bed for experimenting various things. So there is a very nice book called System Performance by Brendan Gregg. If you want to experiment, maybe while you read disk and file system performance chapters from that book, if you want to experiment something, you can use this kind of a setup. So, I mean, the crux is that as your load increases, and any kind of load on these physical components, you end up needing more and more of those. Like we saw here that maybe if 17,000 IOPS is the limit that this disk can support, and maybe you want to support 1 lakh IOPS or 50,000 IOPS, you will need 3 or more disks, and this applies to all the components we saw, like CPU, memory, disk, and network. When you reach capacity and you want to serve more and more requests, you need to split those requests into more and more components. But that's when another tricky probability thing that comes in your way. So I mean, let's say very simplistically, we say that instead of that single node which we called as a DB, and we generically call that as a DB, it can be any component that's stateful. So it can be a file system, it can be a database, it can be anything else, a distributed storage. So we say we add more and more of those physical components so that requests are split um, across those. And this again has the assumption that when you split requests, they are equally split across all three in here. And we need to keep track of all these assumptions that we have, because even in a very well designed distributed system, if you don't partition your requests properly, and you have like a 100 node cluster, but 90% of your requests start going to only one node, then all of that design is in vain. So these assumptions that are done for designing these systems, I think we need to keep track of. Now, when you start using more and more of components, this probability starts hitting you hard. And we'll do a very simple, fun exercise, but this is a very simple probability calculation. Like in 10 standard probability, probably you will. I'm not very good at probability. By the way, my book had a small mistake in probability calculation, so but let's say a disk fails once in 1,000 days. So your disk lifetime, let's say mean time between failure of your disk is like 3 years approximately. So 3 to 5 years disk will be fine. Then what is the probability of that disk failing on any given day, like from today to 3 years? It's very small. It's like 1 by 1,000. That's how you will calculate that. But now let's say you have 10,000 disks, each individually having this probability of failing once in 3 years. And then if you want to calculate what is the probability of one or more disks failing on any given day, you'll be surprised to see that the probability comes out to be very close to 1. And that's very frightening in a way, because I mean, in a typical data center where we run our software, there will be hundreds of thousands of disks, not just 10,000, right? And what this simple calculation shows us that it means at any given moment or on any given day, many of those disks must be going down. And this we did only for disks. Now you consider all the other components that we talked about, and we talked about only these 4 components. There are additional components that a typical data center will have. It will have a power supply, it will have cooling systems, it will have mechanical racks where servers are hosted, and many of those. So a frightening reality of this data center kind of setup where you have hundreds of thousands of components is that on any given day, a part of it must be going down, experiencing some problem. And this is, by the way, reality. At least in 2009 this was. So this is a slide that I directly borrowed from Jeff Dane's talk in 2009. It's an excellent talk, and it's a huge slide deck that he has. If you have heard of latency numbers that every developer knows, that's also one of the slides from that talk. This is another slide that very few people refer to. But this talks about, so that the talk essentially is about his experience in setting up Google data centers in early 2000s, and what kind of experiences and numbers he saw while data center setups were done. And this is something that the numbers that are listed there is, he said, what happens or what you experience in a typical data center in the first year. And if you see those numbers, you'll be surprised how YouTube and Gmail is always up, because you see like thousands of machine failures, number of racks going, and rack, you know, I mean, if you just search on Google to see data center photos, you will see how data center is set up. And it's like similar to how in a library you have book racks. There are racks with servers stacked up. And a rack going down is a big deal because you will probably have hundreds of servers on that rack. So all those are disconnected, or all those are going down in one go. And this is the reality. I mean, you can't change this reality. Some of the outages that we experience, like Cloudflare, is a very good example nowadays of of outages, because they seem to be getting outages every now and then, and they publish blogs which are very informative, by the way, about, I mean, the current outage that they had like last week, I think. It was not because of any saturation, it was a software bug that they had. But outages do happen because of these kind of things as well. And then we are in a dilemma now, right? On one end, we are saying that if we want to serve more and more users and requests and play within the limits of physical components that we have, the only option we have is to have use more and more and more of them. And on the other end, we are now hit with this reality that when you have in the quantities of tens of thousands of these physical components, which typically exist in a typical data center, then you need to deal with this kind of reality that on any given day, a disk attached to your server can go down, or your entire server can go down, or even if you have a cluster, that entire cluster can go down. And we need to then write our software in such a way that that works with this reality, but it masks those failures from the end users. So we saw two things. One is you distribute your requests across n number of physical components, but that's not enough. What you also need to do is write your software in such a way that masks these physical failures that you are experiencing. And physical failures meaning as simple as a disk failure or a single server failure to, let's say, entire rack getting disconnected. Or in the worst case, you might have heard these globally distributed databases that are advertised nowadays with multi-data center setups, which allow you, even when a single data center goes down, they will give you availability guarantee. So, and that's what, and this is what makes distributed systems tricky to implement and also interesting to study and implement as well. That distribution of a state is very easy that way, because you can just do a round robin, I mean, very simplistically, and that will work in most of the cases. But masking failures is my God, it's the trickiest part that complicates stuff. And what we'll do now is maybe we'll take a quick 10-minute tea break, and when we'll come back, we'll see three examples, essentially, as I said. One, that of a distributed file system and how it masks some of these failures. Then we'll see a slightly higher abstraction level of replicating data, which is Kafka. And then we'll see something like Kubernetes, which is more generic implementation. Cool. So we'll take a quick 10-minute break for tea. Thank you. Okay. Shall we get started? Cool. So, as I said, to start with, we'll first look at what is generally called as an object storage and how that's built. Object storage is, you must have heard Amazon S3. S3 is object storage. The open source variant of it is MinIO. Pretty standard. So people who don't use Amazon and have their own data center and want to expose S3 like object store API, they will use this MinIO. And what object store allows you essentially is obviously it stores objects which are essentially files. So you can upload let's say a video file or a audio file or simple text files. And they allow you to have very cheap but large storage in a data center kind of a setup. And the interesting part of that storage is that they store whatever you upload in such a way that it tolerates partial failures. And as we said, partial failures can happen at an individual disk level, or individual server level, or the entire rack level, or an entire data center level. So you might have heard of some disk replication techniques like RAID, and there is like RAID 0, RAID 1, RAID 2. But what it allows you to do is you will typically do that replication behind your disk block interface, which is attached to a single server, and it will tolerate a disk failure but not a server failure. And for that reason, the kind of storage solution you need is that if you are keeping multiple, I mean, one of the things is you to mask, the way you mask these failures is essentially you keep multiple copies of whatever data you store, so that even if one is down, you can possibly get it from the remaining. And because you cannot rely on disk level techniques, you need to tolerate server and rack and that kind of failure. You need a file system implementation which stores your data across servers, which are across racks and maybe across regions. You might have heard of a term called availability zone in a data center. And what that availability zone means is that the set of servers which are in independent availability zones, there is less chance that they will fail for the same reason. So they will have independent power supplies, independent network, and they are as isolated as possible. So the way these object stores store your file is that they divide any file or what they call as object, which is a standard byte array. So they don't care if it's a video file or a text file or anything else. They divide that file into chunks, and there are a set of algorithms called erasure coding algorithms. So they process those chunks with that erasure coding algorithm, and then they store each chunk on a separate server. So what they logically call as disks are essentially separate servers where they store that data. And this erasure coding algorithm has this advantage that if, let's say, you store, you break your file into 10 chunks and run it through this erasure coding and then store it. Even if you, there are different kinds of chunks in the context of erasure coding, and I won't go into detail of those, but we'll see, we'll actually use it and see how it works. there are actually your data bits and what are called as parity, data chunks and parity chunks. When we'll see that. So let's say you divide whatever your object is or a file is into 10 chunks, and 7 of them are data chunks and 3 are parity chunks. You can reconstruct this entire file content even when let's say a small number of chunks are missing. So if you make sure that you divide your file into 10 blocks, store it on 10 different servers, at any given point in time, even if let's say 3 of them are down or you are unable to reach, that means you never get those chunks back. You will be able to reconstruct those missing chunks from the remaining 7 chunks of data that you have. And this allows you to tolerate partial failures. I mean, this is one way to tolerate partial failures at an individual object level. So, so we'll see how this works. And if you go through, so what we'll do is, while we discuss erasure coding, we'll also, I will just point you to the actual open source product that then you can go and deep dive into. But in our repository, we have this project called erasure coding, and it uses a Java version. So Java implementation of erasure coding is this Blackblaze erasure. I mean, I just found it to be the most used. And we have a very simple implementation, just a single file implementation called erasure encode. And what this does is it takes any input stream, so any file you can upload, it runs it through this erasure coding algorithm and creates n number of shards. So, yeah. Right. They don't use this. It's a block level application that they do. Yeah. Erasure coding is used. Min.io erasure coding is used.
So basically, it improves the efficiency with less storage.
So it allows you to, it increases efficiency with lesser storage. Yeah, so it seems to be the most popular nowadays. This is getting popular. And I mean, why I took object store as an example is that you will see nowadays more and more distributed file system APIs. Like in the cloud, you will find HDFS file system APIs exposed over S3, right? And most of the big data products like Databricks, Delta Lake, they are designed with object storage in mind. So they give you transactional table kind of abstraction on top of object store like S3. So and that's why I just used this. So what we'll do is we'll go through the test. So there is this test, and what we have is a simple video file, which is I just checked it in. It's I think a large, not that large. It's 30 MB video file, and we'll try to play it. You can try. I mean, it's a real video animation film. Where is it? Yeah, so this is a very popular open source animation film. I see a lot of networking classes use this film for giving assignments on networking. So what we will do and what that test is doing is essentially we divide this file using that basic erasure encode implementation into multiple chunks, and then we delete some of the chunks, and we try to reconstruct this file, and we should be able to play the reconstructed file similar to, I mean, just like what we just did. So if you go,
Solomon is very popular in the communication system.
is it? Yeah, I'm not.
Communication, the packet loss happens.
Right.
So they reconstruct the loss packet.
Reconstruct the lost packets with this. Yeah.
So basically, the erasure coding is underlying is read Solomon.
So yeah, right now, I mean, what I have used is read Solomon. Yeah, because in Java I found only that one. So what you can do is maybe just take some time to go through this particular test. And I think I do have exercise. We are not using min.io. So what we have, by the way, sorry to confuse you, but we have our own implementation that uses erasure coding. The API it has is it expects you to upload any file, and it then splits that file into n number of chunks, and then you can reconstruct that file back from the chunks, from those chunks. So the code that we have is very similar to the core storage interface of or storage implementation of min.io at object level. So I mean, why I showed min.io code is that if you so if you go through this erasure encode code that's in our repository and understand how this encode and decode works, then you can go to min.io codebase and understand what that's doing. So min.io is just for relating it to a real production ready software that's using it. So what we'll try to do is and you can even debug, I mean, however you want to experiment with this code. No. It can be. Yeah, okay. So that's a good question though. So there is this thing called block size, which is 1 MB. And this is just to demonstrate that whenever object storage is exposed interface, like you upload any object and they will split it into shards, you obviously cannot expect to get that whole data in one go, because you can be uploading, let's say, a file which is 1 gigabyte in size, which is streamed into your code. So the way you need to implement slicing that file is to read one block at a time, which is small enough so that it doesn't overload your your server. So what we are doing here is even if this video file can be of any size, we are reading it in 1 MB chunks, splitting it that 1 MB chunk into 4 plus 3, 7 blocks, and then streaming it into write. So this is a streaming implementation that you will typically find in any production. And the reason for doing this is if you just read about Reed Solomon or try to write a test for it, the examples you will find are like the entire byte array file is read into a byte array, and that whole byte array is chunked into blocks, and then they are stored. But that never works in practice because you can't load entire 1 GB file. I mean, you don't have control over how much size that data will have. So you need to read it. You need to always expect that any object that's stored or retrieved is a stream of bytes, and you read it one chunk at a time, which is manageable. And this is exactly how, if you see Mina.io, or I'm sure if someone gives you source code of Amazon S3, must be doing something very similar. Cool. So essentially the assignment is that this decoded file that we are getting, right? We are getting a path there. We need to play that like this. I should have printed this path, just a sysout. And I can just comment out that delete. Okay. So yeah, I'm not accepting the name of the file, just accepting a stream. So I have named that file as a eraser decoded bin, not a MP4. I can add a to do in here to So I should have also printed this shard file paths. Is it printing it? Do you see shard files getting? Not printing it. So you can print. I think result has shard files, right? Right. So you can see that the video file that we uploaded got sliced into these shards, and we reconstructed that as a bin file. So to play it with a MP4 player, I need to rename it. Sysout. So in the test, so you can see that the encode, encode gives you a result object which has list of shard files where. So I mean you can add it here as well. Yeah, yeah. Common place where I dump this code. Okay. Yeah, I can. I can paste this code in WhatsApp group if you want. Or is there any other way? Huh? Paste what? Oh, paste bin, is it? Or I can check this in. That's easy. Yeah. Right. Yeah, I just. So you can see that we actually created 7 chunks, out of which 3 we deleted. And I hope this plays, but no, it's playing. Yeah, I did. Just a minute. Yeah, I did push it to the main branch. Possibly we could have also done it with some utilities to split and decode again. I just wanted it to be a JUnit test, so just did it programmatically. I mean, the way this test is doing it is just asserting that the decoded file content and the original file content is exactly the same. No, do you have this sysout? No?
Sysout is not printing when running the test. In the build.json.
Oh, in the Gradle it okay.
Show standard stream as
And you don't have IntelliJ, is it?
So in test logging section you can add show standard stream as true.
Where you can add? I mean, maybe you can. If you run it through Gradle individual test, then sysout won't come on standard out. Yeah. Yeah. You can put it on the.
I just have a question. Even
Yeah,
if
yeah.
I pass any file, then like it will be like broken down into any number of.
Yeah, I mean that's configured there. I mean, I have 4 and 3.
Yeah, but the number parity shards is always 3. Is that so?
No. You can have more number of shards. Yeah.
But it's not like per file it's a different number.
No.
of parity shards. It's
You will
always
typically
fixed.
have it configurable for the entire.
A file can be like broken into like 20 chunks, but
Yes.
there should be at least like 3 parity ones. Only then you can like.
At least a few. So the number of failures you can tolerate is equal to number of parity chunks.
Okay, cool.
Unmesh, does the test result get cached or something because the first time you ran it and after that it's like it's even though the system not out is there we are unable if you see here.
No, I mean you are running it through Gradle, is it?
Yeah, I'm running it through Gradle.
No, Gradle won't print sysout.
Oh, okay.
Gradle won't show. No, it won't.
Then how do we get that?
So he did something.
Acha,
You are putting it on the chat, is it? Okay. This is VS Code, is it? Or
yeah, I should think so.
okay.
I added this thing and I'm not that good at Java. That's
Yeah.
most SREs are.
Yeah, Golang. I should probably should have done it in
example
Golang.
is good. It is like
Yeah.
limited understanding of Java.
Yeah. No, Gradle is tricky. I mean, even I get stumped many times by.
Yeah. So for example, let's say if a file is broken down into let's say like 3 shards.
Yeah.
And my parity shard is 3. So
Yeah.
Like
Then you can delete any 3, and it will still be able to reconstruct. But if you delete 4, it won't be able to reconstruct. But if you change your parity shards to be 5 and total shards to be 10, then you can delete any 5.
got it. But
And
like if the number of shards and the parity shards are like same, then
no,
technically no way we can like recover it.
yeah. No, you can. I mean, you can still tolerate. So the total number of chunks that it will create is equal to your data shard number plus parity shard number. So if you have 5 and 5, it will be total 10 chunks which are written, and then you can delete any 5. You can try that out. Just make them both 5 and 5, and the test should still pass. Because what test is doing, if you see, is it deletes. If you see delete shard files, it deletes files. The number of files equal to number of parity shards. So if you go inside that delete method, yeah.
So there will always be like some data shards and parity shards. Right?
Yeah, but parity shards are essentially constructed as chunks of your I mean, it will have content from
Okay.
your file.
Okay. Got it.
Yeah.
One question. Traditionally, distributed file systems needed replication of chunk data. So, does
Right.
this rigid coding eliminate the necessity of?
No, it's actually. I mean, you can consider these as replicated chunks only.
Nothing but additional information.
Yeah. So parity is kind of replication only. It has bits and pieces from your original data.
It's a little bit of advanced information technology,
Yeah.
information theory concepts.
So if I give, yeah, I think my code has some bug. So if I give like 8 and 8, as in the Minayo code base, it works. If I give 5 and 5, it doesn't. There is some bug in my code, maybe. So, so each shard is written to a file, and then input file you read block by block, like a block of 1 MB. That each 1 MB block is split into shards, and those shards are written to different shard files. So
basically every shard has some, like as a chunk data, right?
yes,
Some part of the data.
yes. And so you need to when you stitch it back. Essentially, you read one, you construct one block because you know how much to read. You know the shard size, the number of bytes for every time you chunk a block. So number of bytes in a shard, you know. You read those many bytes. You read it from all, say whatever, in our case 5 or 6 or whatever number of blocks. Then you reconstruct that block of 1 MB and you write it to the output file, and you do it for all.
So there are so I thought initially that there will be 7 total shards per block. So
Yes.
number of blocks into number of shards will be the total number of files.
No.
That's not the
So number of files is per shard one file.
one only.
Yes.
All the blocks are within one shard file itself.
So each block is split into number of shards, and each of that chunk, each of that shard chunk shard goes into that one file.
So it's like an ongoing writer.
Yeah. So you keep number of shard files limited. I mean, it will be 7. But you can read, there can be, say, for 32 MB file, if you are reading 1 MB at a time, number of blocks will be 32 that you read. You will read 32 times from that file, from same file. And the reason you do this is you keep the amount of data you process in one go is only 1 MB. I mean, it can be 10 MB or more as well, but it limits the amount of resources you use. You don't need to like read entire file in one go. Yeah. Yes, it is in the test only. So,
The second step is that we have to change the helper, right? What do we have to change here?
no, you don't. I mean, you can. You don't need to change anything here.
But the exercise says that, right? Edit the helper, delete shard files. Second step.
Line 7.
Yeah. 17.
That, I mean, if you want to try out removing different files in every run, because right now it's just removing sequentially 1, 2, 3, 4.
Right, so we've done the first step. That
Yeah, I mean, second is ignore. You can ignore that because we are already deleting something in there.
we directly move to third one.
Yeah. So third is something that I just checked in. So we essentially just need the file path, and we need to. Yeah, actually, it's not a very good way to give exercise, but yeah, I wanted to have that unit test intact, so so that if I tweak anything, I can quickly verify.
There's no
There is no git push. We are doing a git pull. We are not. Have you checked anything new after the first?
No, that one push only what I did. So essentially what you need is the decoded file path so that you can try to play it. And you will need to change the name suffix to be MP4. That's my bad. I run the decode test. Yeah, actually, it's tricky to do it in a unit test because you can remove manually, but then you need to split that test into two two executables. Kind of you first encode, then you go manually to the file system, delete, and then decode. Yeah. Um, you can delete anything. You can delete anything. Yeah. Yeah, I mean, if you delete more files than the number of parity shards, it won't be able to reconstruct. So that's the maximum number of failures that it will tolerate. No, no, it will fail. Yeah, so it won't be able to reconstruct using that Reed Solomon. similar to quorum. So yeah. So if it can't find, so I mean you can now map what we have to how Amazon S3 or Minayo works. So imagine our eraser encode is the compute layer, or the layer that accepts user requests for putting the object, and then you have different servers spread across racks or availability zones, and what we are writing as like 5 files on the not 5 4 plus 3 those shard files on the disk. Imagine them to be written on these nodes, which are remote nodes. So what we are doing as a file write, it will be kind of a file upload. If it's a HTTP API that these servers expose, you will just upload the file, shard file, onto these nodes. And then what it allows you to do is, when you read streaming read, obviously you won't read the whole file at one go, but you fetch from all these nodes, and you can tolerate if you can't reach some of the nodes, which is equal to those parity number of nodes. And you can still reconstruct. So as a homework, maybe what you can try out is converting this into a remote service where you upload on different nodes instead of writing to local file system. The same code should work, because what you need to do is just reading and writing to file. You need to convert it to uploading those shard files or streaming the shard file content onto remote nodes. Yes. I mean, so there is a limit to how many failures. So the key to any distributed system which gives you availability and consistency guarantee is that it tolerates partial failures, and there is a limit to how many failures it can tolerate. So typically you say that if I am operating, let's say 10 server cluster, then 3 or 4 I can. If more than that goes down, then you are in trouble anyway. So the way you size the cluster typically is driven by how many number of failures you want to tolerate or you can tolerate, and you need to make sure that you physically place your cluster nodes in such a way that you can achieve that in practice. For example, you know that in a quorum based systems, like if you are using Kafka or Zookeeper, and let's say you have a 3 node cluster, and what that 3 node cluster means when you use quorum techniques is that it can tolerate 1 failure. So you read and write from majority and it tolerates 1 failure. But imagine if all 3 nodes are on the same rack in your data center, then all 3 can go down, and then it won't be enough for tolerating your or giving you availability guarantee. So you need to know how many failures you can tolerate with the design and topology that you have, and then you need to physically place those nodes accordingly. Okay, just a quick time check. We are at 12, almost 12:25. So what I will do is I will introduce next section, and then we'll take a 10-minute break, and then when we are back we'll do this Kafka assignments. So what we saw is one example of how partial failures are tolerated. And the way it was done was at an individual object level or individual file level. But a lot of times you need a little higher level abstraction where you tolerate. So in case of RDBMS, for example, the logical abstraction for storing your data is a table. In a message broker, it will be a topic. In a pub/sub kind of a model, topic where you publish data and subscribe to. And in these kind of systems, then you require this level of fault tolerance at that logical data storage level. So you require, if you are building a message broker, for example, you will expect fault tolerance at a topic level, not at an individual message level. If you are building a database, then you expect fault tolerance at a table level, not individual row level, for example. And we'll see an example of Kafka-like message broker, which uses standard replication technique for replicating your data. Other slight variation from the object store that we saw and a database or a Kafka-like message broker is that when we provided fault tolerance at an object level, the expectation was that that object can be of any size. So we kind of did our example with a video file. When we build database or message broker like Kafka, generally the expectation is that individual data items will be smaller in size, maybe kilobytes or few megabytes. They won't be, a single item won't be like a gigabyte size, right? So when we insert data into a Postgres table, for example, individual row will never be 1 gig in size. Your entire data can be, which is say millions of rows. And when you have these kind of systems where you have multiple smaller items that you store in some logical entity which groups that data together, generally a lot of these records data records that you store will go in single file. So right now we had like one object, one file. In case of Kafka like message broker or a database, one file will have, let's say, millions of messages, and what we will fault tolerance that we will provide will be on that one chunk, one file. So we'll take a quick 10-minute break, and then we'll look at this section 4, which is essentially a small Kafka message broker. Actually, this Kafka and Kubernetes is a bit too much to cover in 1 hour, but because we have like 1 hour for Kafka, 1 hour for Kubernetes. But what I expect to do is at least give you pointers and a code base which is fully functional, which you can, you can study at your own pace later. Cool. So we'll be back by 12:40. Yeah, yeah, yeah. I think we'll be able to. Oh, wait. We are eating so late before lunch. start in 5 minutes. 2 minutes actually. No, but I can do that maybe in a lunch break. Cool. So let's get started. Um, and what we'll see now is Apache Kafka, and very similar to what we did with our miniature erasure coding code snippets. What we have here is so this module 4 or section 4, which is divided into 4 modules. what these four modules have is it's essentially step-by-step building a distributed message broker like Kafka. So this module 4 is a fully functional distributed message broker. And I will just walk you through this test. There are a few assignments. I don't know if you'll get a chance to complete all the assignments in 1 hour. We'll try to complete as many. There is in the same repo there is a solutions branch. So what you checked out is the main branch. There is a solution branch which has all the exercises solved. So exercises are very small actually. You need to write like complete some code snippet that you need to fill in. But if you don't get a chance to complete all the assignments, you can refer to the solutions branch which has all the code snippets working. But what this integration test, this is the end goal that we have to make this work. But what this does, and I try to do it for any distributed system that I want to study, is I write code in such a way that in a single test I can set up a cluster and then orchestrate that cluster in a JUnit test and then verify the results. So what this producer consumer test is doing is it starts embedded Zookeeper. Have you heard of product called Zookeeper? Kafka used to use that, and practically all big data products they use that. So it starts embedded Zookeeper, because our miniature Kafka implementation also uses Zookeeper, similar to the real Kafka. And then it starts individual brokers again in an embedded way. So when you say new broker, it essentially picks up a random port to listen to, and then it starts that broker in the same test. And then what you can do is you can start your cluster like this, like start individual brokers, and then run this create topic utility, which is working with actual Zookeeper for storing data, and we'll see how. And then you can experiment producing a set of messages and consuming them from a consumer that we wrote for our own miniature Kafka. So this is not real Kafka consumer and producer, but something that we have coded, very, very simple consumer. If you see here, it connects to the set of brokers and tries to fetch data. So now to understand what this code is trying to do, let's quickly talk about Kafka, and it's also a good example of how a typical distributed system is built, which has two parts to it. One is the actual data and data distribution that you do, and the other is managing that whole cluster itself that you need to do. So let's say your cluster has 100 nodes, and you add 10 more nodes, and some of them are failing or get disconnected. You need someone to track all this churn that's happening in your cluster. Someone also needs to keep track of how your data is mapped onto this multiple nodes that you are running. So we saw in erasure coding that we divided that file into 8 parts, 4 or 7 parts, whatever. One thing that we did not do there is because we were using this just our local file system to store all the files, is we did not have any tracking of this metadata, that for a given object or a file that's uploaded, how many chunks exist and on which servers those chunks are mapped to. That we did not do, but in a real cluster we need to do that, and Kafka we will use as an example to see how that happens in practice. So Apache Kafka is a distributed pub sub system, so you expect to exchange messages between entities which are called as producers and consumers, and the way you exchange those messages is that there is a logical thing that you declare, which is called as a topic, and then your producers and consumers can have this contract that producers will produce messages on a topic and consumers will consume that from a topic. Now I briefly talked about the need for doing cluster coordination and metadata tracking, and this requirement is there for all the distributed products, not just for Kafka or Minayo or Cassandra or things like that. And these products like Zookeeper came from Yahoo as part of all the tools that they built for big data processing. But a similar product exists in Golang community called as etcd. So Kubernetes and all the other Golang based products like distributed databases like CockroachDB that are there, they use this etcd for the same purpose. And what these products do is they provide you with all the basic functionality that's needed for a consistent view of metadata about the cluster, how many nodes exist, which nodes are currently active, how the data distribution is mapped onto nodes. If some node is up but it went down, then notify that okay, this went down. Allowing to do things like leader election. So when you have a data cluster and you want one of the nodes to act as a leader, you need to run something called as leader election, and you need some facilities to make it easy to implement leader election kind of algorithms. So these products like Zookeeper and etcd, they essentially provide all these basic building blocks for doing all these things. At very high level, Kafka essentially looks like this, that whenever you set up a Kafka kind of cluster, you have a Zookeeper cluster that you need to first set up. In the newer versions of Kafka, this Zookeeper is replaced by their own consensus implementation called kraft, right? But conceptually, it's exactly same as Zookeeper. So it provides the same facilities that Zookeeper provides or used to provide for Kafka. And then you have your data nodes, because it's a message broker, in that domain these are called as brokers, which essentially allow you to have these logical entities called topics, where your messages can be produced and consumed from. You see that along with topic we are mentioning partitioning, because one of the first things we saw in the need for building a distributed system is to be able to partition your data so that different users can go to different parts or different nodes, to make sure that single node and single set of physical components don't get overloaded by that. So even if we say that topic is our logical thing where you produce and subscribe messages from, in reality that topic is typically partitioned across multiple nodes, and obviously that individual partition as well needs to provide fault tolerance, right? Because if I have partition 0 or 10 partitions, and partition 0 goes down, or the node on which I have partition 0 that goes down, I still want the subscribers who were interested in messages from that partition 0 to be able to get those messages. So this each individual partition is also replicated on multiple other nodes, and that's why you see individual partition also has this leader and follower, and we'll see how that happens. Other interesting thing is that there is one node amongst the set of nodes that run this broker, which is tagged as a controller. And are you aware of Kubernetes architecture? So Kubernetes also has this thing called controller, right? And we will see after lunch in our Kubernetes part. But what this controller does is it uses Zookeeper to track failure of nodes or addition of nodes to the cluster, and then it takes decisions on behalf of the cluster. So for example, if it detects that, let's say, this broker or this node has gone down, and then it knows from the metadata stored in here that this broker 3 actually had topic A partition 0 and leader for partition 1 and partition 1 for topic B, for example, then it needs to make sure that whoever is relying on this data, they are now directed to some other copy that exists somewhere else. So if topic A partition 1 leader was here and topic A partition 1 follower is on this node, and if this goes down, it needs to then maybe make one of these two as the leader, so that any subscriber or producer using this partition 1 for topic 1 can now go to this broker or that broker, depending. So that cluster-wide decision making, this one needs to do. Now, to be able to do that, you first need to make one of the running nodes or running brokers as a controller, right? Because this controller, if you see, it's not any separate process that's running outside of your cluster. It's part of your cluster, and one of the nodes is just playing the role of the controller. And what it means is that just like anything else can go down or get disconnected from the network, this node that is playing the role of the controller, even that can go down. And if that happens, you also need to provide fault tolerance for that role. And so if this goes down, you need now two things to happen. One of the remaining brokers or one of the remaining nodes, it needs to now play the role of that controller, and then it should do the same thing that this controller would have done if it found out that broker 2 went down or other broker went down. So now it knows that topic B partition 0 leader was on this node. So it needs to mark topic B partition 0 on some other broker as the leader. So there are two types of roles, or there are three types of roles that exist in a typical clustered distributed system. One is your standard data nodes, which are brokers in case of Kafka. Two, someone who acts as a metadata store and providing basic facilities for cluster coordination. And third is a cluster level controller which takes decisions on behalf of the cluster when it detects changes from this entity like Zookeeper. So there are three things like this. There is fourth important thing that and we'll see how that happens, is about how you replicate data. In the erasure coding example, we saw that you split it into multiple chunks and each chunk is placed on different servers, giving you the effect of replication. In products like Kafka and databases, what we do is each partition where you are actually storing data, actually storing messages, it needs to be replicated on multiple other nodes, and which is typically you will see that count which is called as a replication factor for your topic and partition. It will generally be 3 or 5. So when a producer produces message on topic 1 partition 0, it will also be copied to topic A partition 0 follower on broker 3 and its follower on broker 4. And when you distribute or replicate data like this, and also need to give a fault tolerance kind of or also need to achieve fault tolerance. And what fault tolerance means is that if any of this goes down, you still should be able to serve data from the remaining nodes. Then there are tricky issues of consistency, and we'll see in some time why they appear. So this is the overall architecture, and we'll see step by step how we can build something like this. We'll start by two basic assignments or two basic things. One, how we manage group membership, and what that means is that how we store data in Zookeeper about the number of brokers that exist and what metadata about the brokers we store in Zookeeper and how that happens. And second is when we say we store data in topic partitions, how that data storage happens. And after that, we'll see how the replication of that data happens. So if you look at the So we'll maybe start with module 1, and I think I do have exercise. Okay, there is exercises. This module 1 has nothing fancy but just this class called log, and what this log is nothing but just a wrapper around a file. And it gives you two methods, one called append, which accepts a key and a value, which is any generic byte array for key and a value. And then it also gives you a method to read message at a particular offset. And what this offset is that every time you append to the file, you assign a logical sequence number to that data. So the first message that's appended will be given offset as 0. The second message that's appended will be given offset as 1, and so on, and so forth. I think I do have some. So the assignment here is essentially just to, so there is a corresponding test which is essentially storing and retrieving these messages. So we have to make this test pass. Currently it is failing, and there is a hint in here. So logically what's happening, and you can refer to the code as well, that let's say we have orders topic where we are producing messages whenever order is placed, right? So that message will have, let's say, a key called order ID, and then whatever order data you are producing, and you are appending it to the file, right? You just keep on adding it to the file. Now, when a consumer needs to consume it, it needs to tell you from what point it should start consuming the message. Because let's say you have 1 million messages. Not every consumer will want all 1 million, right? Some will want from the beginning, but maybe some will want only last 1,000, right? Because they have already consumed a set of messages. So just writing to the file is not enough. We also need to somehow track that messages to the position in the file, or map those messages to the position in the file where those messages exist. So when you append to the file you can imagine to be a single byte array kind of a chunk, right? I mean, it's a binary structure. And when you keep on appending to the file, if you see file system API, when you append some data to the file, add some data to the file, or write some data to the file, you get corresponding position in that file where that data is written, right? And if you want to read, say, message 3, then what you need to do is you need to open that file, go to position 56 in that file, because maybe 56 bytes are written in first 2 messages, and then read one message. So you need some way to figure out what I call as message 3 actually is written at position 56 in that file. So you need to keep an index that maps this monotonic 1, 2, 3, 4 numbers that you assign to the messages to the location in the file where that message is written. And so you will find that any time data is written to file like this in append only log, you also need to keep another mapping which is called as index, very similar to how databases, databases, you can declare indexes, right? They're different than this kind of indexes. I mean, but essentially what they do is they map a logical data key to the location in the file where you can directly jump and read that data. Otherwise you need to do full file scan or full table scan. And in case of database, a table is a file, so you need to do full scan. So that,
For consumers and consumer groups,
yeah,
they need to maintain last to right position or something.
yes.
So that also they need to maintain.
but that's outside of this. Yeah. So that becomes then responsibility of each consumer to know till what point I have read. And now Kafka provides you that facility that you can commit offset for each consumer. That's within Kafka itself, not outside. But the basic log or a topic partition implementation is like this. So what we have to do in 5 minutes is to make that test pass, because that will force you to go through the code to see what's happening there. And that append method you see there, right? I mean, essentially when a producer produces a message, so your producer client that you use when using Kafka, it has method produce on it, right? In the end, when it's actually stored, this is the method that will get invoked, essentially. And this is our own miniature Kafka, but if you, I should maybe open, I'll open in some time. But if you see real Kafka code, if you go to GitHub and clone Kafka codebase, you will find very similar looking code in there. Yeah, I mean, you will typically have an individual file divided into segments, and then you will clean up periodically, so you don't keep on building. Yeah. Typically, it's 7 days, I think, in Kafka.
When that cleanup happens, even that hash map that used to track the offsets
Aha.
should also be updated.
I mean, you need to remove some data from that.
But even the position in the file, that will also change, right? File name changes. Log name, logs you are having.
No, so what happens is
I mean, you can delete, let's say after 7 days, you can configure it to. Internally it does it, yeah. But it will need to, yes, clean up that index map as well. Because one other thing is that, so right now, if you see in this code, what's called as offset index is stored in memory in there. But this, obviously you can't store all in memory. So this index also needs to be a file on the disk. Yeah. And that needs to be cleaned up as well when you remove data. This is append only file. No, not that, but the cleanup. See, the thing is that if you keep on appending, and let's say you keep your server up and running for 6 months, and if you are getting like millions of messages daily, then what will happen is your size of that file will grow into, say, terabytes. And what you need is some mechanism by which you maybe remove some unused data.
so sort of cleanup and compaction.
Cleanup and compaction. Yes. So you don't update what is already appended, but you clean up. Right. So you don't update once a message is produced. You don't update that. But yeah, that was not your question. Yeah, that index needs to be cleaned up as well, is what I see. Yeah. Actually, I have a comment here saying call write to file. So you have to just make a call to the method that already exists. So what I have opened is actual Apache Kafka code, and you can see that like very similar to what we have. This very basic log append which writes to file. Obviously, this is very complicated, but it in essence is exactly the same code. So you say this memory records. What you see there is essentially the a set of messages which are produced by the producer, and the file channel is the file where those will be written, and this is almost exactly the same code that we have, where we write to the channel. And the way it manages indexes is you will see offset index. So this offset index is essentially the place where it manages that index from offset number or message number to the file position. And as I said, it's not, you cannot keep all of that in memory in a in-memory hash map, because you need to persist that, and that's what this does. But again, conceptually the same thing. So did you get that basic log test working? By the way, this log that we just saw is almost exactly like how write-ahead logs are maintained in databases as well. Have you heard of this term write-ahead log in databases? Like even single node databases like Postgres do have write-ahead log. So if you open any database code, very simplistically say Cassandra like database code, you will also find very similar code where you have append only log, where you store whatever data you need to store first, and it's managed in a very similar way. So we'll see next piece now, where what we saw was like a very barebone storage layer where we added our messages and read those messages back. But when we are managing cluster, as I said, you need to somehow store your cluster metadata into Zookeeper. And when we say cluster metadata, very first basic information that we need is how many brokers or how many nodes are part of the cluster, and what is the IP address and port of those nodes, so that clients can communicate with them. And if one of those goes down for some reason, we somehow need to know that this particular node has gone down. So when you use Zookeeper for doing this kind of cluster metadata and group membership management, you expect every broker or every node that's part of your cluster to register itself with Zookeeper. And we are saying broker needs to register with Zookeeper. If we are building something like Kubernetes, then Kubernetes nodes need to register with API server in Kubernetes, which is backed by etcd. So different names we will use, but they are doing exactly the same thing. So if let's say we have this 3 node cluster that we are managing, we need to name each node by generally given an ID which is unique. So broker 1, broker 2, broker 3. Each one at startup will register with Zookeeper. And what this registration will look like is that, because the second part that's important is if one of these nodes goes down or broker goes down, we need to know. So Zookeeper has this concept of so Zookeeper gives you a file system like API. So what you store is expected to be a hierarchic key and a value. So it gives you a key value API essentially, but the key is expected to be hierarchic. And when I say hierarchic, you will have keys which are prefixed like this. So for all the broker related information, you will have a common prefix saying /brokers/IDs, and then you will have data associated with the broker stored there. If you want to store metadata about topics, like how many partitions exist, on which nodes those partitions exist, then you need to prefix it with something like brokers/topics. I mean, you can decide what that prefix is, but it needs to be prefixed like that. And another useful thing that this Zookeeper gives you is every time you store any information, you can mark it either to be a temporary information which is expected to be refreshed every time, or a permanent information that needs to be stored forever. And Zookeeper calls this temporary information as ephemeral information. So it has an API which says that create permanent or store ephemeral. And what it means to be ephemeral is that whatever data is stored as ephemeral data, the lifetime is associated with the client session. So Zookeeper is a client server thing, right? So Zookeeper is a cluster in itself. So when you use Zookeeper client to communicate with Zookeeper, it maintains a session. So it let's say keeps a connection open and periodically sends heartbeats on that. So the data that's created as ephemeral is stored only till the point that this session is alive. But if whoever is storing data in Zookeeper gets disconnected from Zookeeper, all this data will go away, or Zookeeper will make sure that it will delete that data. And this feature is again very common, not just in Zookeeper. So Zookeeper calls it ephemeral, but etcd or any other product which is used for cluster management has concept of leases. So you can associate a lease with the data item that you store, and if it's not refreshed in a certain duration of time, it is deleted from the data, from the store. And generally, when you want to track group membership in the cluster and need to know if a particular node is alive or not, you use this ephemeral type of data to store information about that node. So the IP address and port that we will store for each broker, will store that as a ephemeral data. And how it helps is that if say broker 1 stores ephemeral data as broker ID 1, IP 10.10.10.10 8080. If that broker 1 goes down, that data will disappear as well. And if someone can track a particular key prefix, so a key prefix in here is let's say this. So this is the constant key prefix, right? So every broker will store data with this key prefix. If I can track a key prefix saying any changes that happen in key value data with this prefix, notify me. Then anytime a broker goes down and a corresponding key value with this prefix is deleted from Zookeeper, I can get notified saying there is a change in this key prefix. And if I know what already existed and what exists now, I can get the delta out. And because this information gives you the number of brokers that exist, I can derive which broker has failed. So this is the basic implementation pattern for managing group membership and failure detection. We'll see in Kubernetes as well how this is done. But the second assignment was, and I think we'll do it together, was to make this in the module 2. There is this test called broker registration test, and what this broker is essentially the log that we created in module 1. Now we are wrapping that with a layer which has a network API so that clients can talk to it. So it wraps that log with broker or network API, and it also has a layer that talks to Zookeeper for storing its own information. And you can see that when we call startup on this broker object, and you can imagine it to be a main method on your broker process, which starts a new process. It uses this Zookeeper client to register itself, and the data that it stores or metadata that it stores is broker ID, host name, and port for this particular broker. And the assignment here, what we had was store this information as a ephemeral data in Zookeeper. And if you just call this particular method, so that create ephemeral path is already in there, and then try to run all the tests in broker registration, you will see all the tests are passing. And what these tests are really doing is, as I said, the tests run an embedded version of Zookeeper. They use Zookeeper client to talk to Zookeeper for storing this data, and uses Zookeeper API, real Zookeeper API. And then it also uses that Zookeeper client to fetch data from Zookeeper. So it essentially expects that when broker starts up, there needs to be some data for broker ID 1 in Zookeeper. Is this too much of an information overload? Hopefully not, but it is. I mean, it's very hard to cover in 1 hour. It was my ambitious goal to show like everything together, but so see if this test passes, and we'll quickly go to the next one. Okay, so there are two more things that we need to talk about before we go for lunch. Now, one is that sorry, yeah, I mean we can discuss after the or in the break, because there is a lot of stuff that I'm talking about. But there are two more things. So what we have till now is a basic place where we can store messages, which is the log file. Then a simple wrapper around that log, which has a network interface to which clients can talk to, and which itself talks to Zookeeper to store its own metadata. And now we need a facility to create this logical chunk called topic, right? So if I want to do something like create a topic called transactions, where I produce all the transaction related messages. Now this logical thing that is called as topic, as I said, is essentially divided into partitions. So we need to do multiple things if we need to implement something like or support a concept of a topic, that whenever someone asks us to create a topic, we should be able to divide that topic into multiple partitions. And let's say if user tells us that you create a topic called transactions with 10 partitions, right? We need to somehow map those partitions to the nodes or brokers that we have. And for each partition, we also need to create a replica for that partition. So if let's say I have 3 partitions that I'm creating for a topic called test, I need to store this information somewhere, that this topic test has 3 partitions, 1, 2, 3, and for each of these partitions there is a replica that exists on some node. There is one more thing that we need here, is that depending on the way we are replicating data between these partition replicas, we need to also now in case of Kafka, the way data is replicated is by using a leader follower kind of an approach. So one of the replica is designated as a leader, and any data that's produced always goes to that particular leader. So out of, let's say, 3 or 5 replicas, only one is designated leader, and any client will always go to that. Now it has then the responsibility of replicating data on nodes or brokers which are marked as followers, or it's other way around in Kafka. So there are 2 ways data can be replicated. It's either a push mechanism, where data first goes on the leader and then leader copies it onto followers, or it can be a pull based mechanism, where data goes to the leader and the follower is implemented in such a way that it periodically pulls data from the leader. So Kafka's choice for replication is pull based mechanism, and the advantage it has its consumer is also pull based. So it essentially can use same technique that the consumer uses for its followers. So you will, along with this cluster, you will typically have this kind of a utility or a API that allows you to create this topic and take all these decisions on your behalf. So if you look in this code, there is this code utility called as create topic command. In older Kafka, this was admin utils. So whenever you run a utility to create topic, there is generally a shell script that wraps all this for you. Internally, it will be executing code like this, and it's again homework for you to go through this code, but but if you there is a corresponding test, I think, for the create topic command. And you see a lot of code there that involves Zookeeper, because if you see the internals of this create topic command, it's doing all the things that we talked about. So it creates these partitions depending on how many partitions we need. For each partition, it creates a replica, and then it stores all this information in Zookeeper, because that's like the source of truth for all the information that exists about all the metadata that exists about our cluster. And one type of metadata is about cluster's group membership. Other type of metadata is about how data is distributed across the cluster. So this topic, or in case of databases, tables, and as we'll see in Kubernetes, it's about how pods are mapped to the nodes. All this is about data distribution metadata that's stored in Zookeeper. And you can take some time to maybe run this test. So what this is doing is actually interacting with Zookeeper to store all this metadata. And also take your time to go through the code that's assigning partitions and replicas to nodes. So there is this replica assigner code, because this is very crucial, because one of the first reasons to have multiple replicas is to give fault tolerance, or to achieve fault tolerance, and it depends on how you distribute these replicas across the set of nodes. So for example, if you need different replicas in different availability zones, this is where that logic needs to be implemented. And for that, you also need metadata for each broker to know which broker is in which availability zone. So it then becomes responsibility of that broker to, when it registers itself, it also needs to register not only just IP address and port, but maybe some additional details about how the metadata is, in what availability zone it is. Yeah, it's 1:45. I think we can take lunch break. Was this too? I mean, it was too fast, I know. But we'll probably continue this, and maybe Kubernetes will just do a cursory look then. I will just walk you through the code that's out there. By the way, in this, as I said, in this repo there is a solutions branch. So all the exercises where the code is, you need to fill in the code or fill in the blanks. All that is available in that solutions branch. So you can check out solutions branch and use that as well, because then you can have the tests which will all pass. Cool. So let's take a lunch break then. Half an hour. Zookeeper itself is a replicated service, yes, and it uses. So I did not talk about it, but I just mentioned, I think, Craft, or no, I did not. So
Graph can be used to do consensus between the brokers to do election.
no. Yeah, let's go step by step. So Zookeeper or etcd, which are metadata stores, they themselves also need to be fault tolerant. And additionally, the kind of facilities like this ephemeral node or lease that they provide, it also needs them to be very strongly consistent, because if I say that I am holding a lease, then it should never ever happen that even if internally Zookeeper is failing or some nodes are failing, someone else gets that lease refreshed, right? Lease or holding a lock, distributed lock, I mean, these are very critical operations. And for that, these Zookeeper kind of products, they internally implement consensus algorithms like Raft or Paxos, or in case of Zookeeper, it's Zab. Now, when you replicate data, like in your partitions, they have multiple replicas, right? There is a similar requirement for achieving stronger consistency. And even there, you can use consensus algorithm within, say, replicas of an individual partition. Now, Kafka doesn't use consensus for replica consistency, because one of the constraints of any consensus algorithm is that it's a quorum based algorithm essentially, and it expects at least majority, so it needs then the concept of a majority, and then it expects your replication factor to be at least 3. And Kafka, the way it is designed, it allows you to even have a replication factor of 2, which doesn't have then any concept of majority. But Kafka's design is that it gives you a spectrum of consistency, so it allows you to have lower consistency guarantees and stronger as well. So you can have a replication factor of 3 plus, but also 2. And none of the consensus algorithms can be implemented with replication factor of 2. And that is the reason replica level consistency is not implemented with consensus in Kafka. But if you look at databases like Spanner or CockroachDB, YugaByteDB, MongoDB, so they use this consensus mechanism for both the things, metadata management, same consensus, but the kind of things that they do there are different, like registering a lock or registering a lease kind of API that they expose, and consensus for even data replication, where it's primarily just set and get kind of operations. Does that answer? Yeah.
Kafka nodes doesn't do any consensus or anything. Does it mean like Kafka number of nodes can be even, or
Number of nodes can be anything.
it need not be like for consensus we will do typically
3 or 5, yeah. But within, so there are 2 levels of things. So one is the number of nodes. Now each node can host multiple partitions from a topic, and for each partition you have replicas. So even if you, let's say, have a Kafka cluster which is, say, 100 node cluster, for each partition for a given topic, the replication factor will typically be only 3. So out of those 100 nodes, only 3 or 5 will host or 2 will host a particular partition, and you can have hundreds of partitions like this.
So one more question. So in Kafka, the scaling is not easy, is what people say, right? Is it because of the partitions?
No, auto scaling is not easy. Auto scaling. Scaling is easy.
Partitions we can.
Now, why auto scaling is not easy is that that's so if you see how the replicas are assigned to partitions. Now this is static mapping. So you have to upfront decide how many partitions my topic will have. So if I say that I want like 10 partitions or 100 partitions, then forever it's going to be 100 partitions. So even if now I face a situation where maybe I'm getting a lot of producers and consumers which are thrashing my topic, and I want, let's say, instead of 100, I want like 200 partitions for that topic. It's not, I mean, it cannot be easily done in
You can increase the partitions, the reduction is not easy.
no, even increase, because if you change the, like, whether increase or decrease anything you do, your mapping of key to which partition that data goes to, that changes. And then if you need to use this mapping in a way that key maps to a particular partition, but if you redefine your partitions, then all that mapping becomes, existing mapping becomes invalid.
A lot of shuffles.
So you need to shuffle them. I mean, it causes shuffle. So if you redefine your partitions, data from existing partitions need to be moved to newer partitions, or vice versa. Even if you reduce the partitions, the same thing needs to happen.
But I think in some cases it allows, like, I need not have any logic. Like my application logic is such that it can go to any partition, then it should be possible for me to
Any partition retrieval is difficult.
Yeah, retrieval is tricky, right? Because you
Can't send it
typically need, so another constraint that Kafka has is Kafka expects ordering guarantee on a particular partition. So any consumer that consumes from a particular partition is guaranteed to get data in exactly the same order that any other consumer gets it. When you reshuffle, if you reshuffle partitions and you reshuffle data, that ordering guarantee goes for a toss, because now you have data arranged in a different way. But that's a constraint because you need to provide this kind of a guarantee. There are other partitioning techniques like what's used in Cassandra. They allow you to grow partitions. If you add more nodes, automatically the number of partitions will be more. So there are techniques like what Kafka uses is called as fixed partitions. You decide partitions upfront, and it allows you to then get this kind of ordering guarantee, for example, per partition ordering guarantee. Or like in Cassandra, what they choose is number of partitions proportional to number of nodes. So number of partitions grow if you add more nodes. They then do need to reshuffle data, but the design makes sure that, I mean, then they need to make sure that shuffling is minimal and evenly spread across nodes, because any shuffling that happens when you add more nodes is can be problematic.
So what they do is fluctuations in the events in a scenario.
No, I mean, so just like you need to do capacity planning upfront, anticipating what kind of load when you define topics, you need to upfront do some capacity calculations to decide on the partition number and also the cluster sizing.
Some people are doing what they're doing is in the producer itself. So in the machines itself, they are doing some buffering.
No, that happens. I mean, you like any time you store any data, right? Like particularly in case of Kafka, which is designed to be high throughput system as opposed to low latency. So they favor higher throughput over lower latency. And for that, what they do is, instead of, like as I said, one of the assumptions here is that your individual data items will be smaller, few kilobytes in size. So it's very expensive if for every write that happens you make a network call to for like few kilobytes of data. So what you typically see happening is they batch, let's say, multiple messages together, and then they, over the network, they send the entire batch, and that entire batch is stored then on the disk.
So the only way is to shut down, make an yeah,
Yeah, not shut down, but it needs to be controlled by an admin because you don't want to like because you also need to take care of you do not want to break consumer expectations, because if you want that kind of for example transactions topic and you have sharded data based on let's say account ID, and for a single account or between or not on account ID, maybe something else which has a group of accounts on a single topic, and then if you add more partitions and that ordering breaks, there might be some consumer expectation that breaks.
If the consumer doesn't expect the data to be ordered, I think we can easily scale up the number of.
Yeah, then you can do whatever. I mean, then the thing is that in Kafka, in every message you will expect a key, and the data is partitioned based on that key. But when you don't need any ordering, you can have that key to be empty, and then your data goes on any partition, and it will be consumed by any consumer. So
I think PubSub architecture itself enforces a notion of order.
yeah, I mean, you do expect an ordering. Yeah. So that's the constraint of a PubSub kind of a thing. Yeah. Okay, it's almost 2. Right. No, but see the logic that we use inside the producer client that we use.
Actually, you need not specify it. Then what happens? That's possible. If you don't specify any logic that you're using, just randomly assign. So in such case, what
No,
happens?
the thing is that you don't specify any logic in the sense the default logic is that it expects a key in each message. Now, if you use that key, the logic it uses is that it will hash that key at modulo number of partitions. So, depending on a particular key or the type of key,
Let's say I take some whatever some attributes.
that's the default default.
No, I mean, you start with 50 partitions. Because let's say even if you start with 20,
As I said, my key is my account ID.
or let me say randomly. Okay, account.
There are two things that you put a constraint on. If make that more conversation. I haven't prepared any PPT.
Okay.
I have a set of talks, a set of code bases. Pick and choose based on interest.
So there is one website called Code Crafters. Okay. So where I just took the subscription, but I haven't started using it. So basically, all these like Redis, Kafka, so databases you can create. So you can practice. And
Okay. You can do it for free with my framework. With the subscription. So I have a framework called Tickle.
what is the subscription?
So yesterday was on time, but I don't know this weekend.
Yeah, I'll check.
Sorry. Cool. So shall we get started? Yeah. So the last thing in here is I will just show you the in this module 4 there is a test called producer consumer test, and which actually binds everything that we discussed so far together. So it allows you to start a Kafka-like cluster, our own miniature Kafka cluster from brokers that we have built. It chooses one of those brokers as a controller. It allows you to create a given topic with a set of partitions and replicas. And then it has a very simple producer and a consumer which produces and consumes messages on that. So what you can do is that module 4 has like all the code that a typical Kafka-like cluster would have, and it's not too big a code. I mean, it's just a few files. You can see that. So take your time to go through that this particular test. You can tweak it by changing, I mean, whatever topic you want, and the number of partitions and replicas. Oh, this is okay. You can even spin up a bigger cluster. Like if you, instead of broker just 1, 2, 3, you can create n number of brokers in a for loop, like a 5-node cluster, 10-node cluster, if you want, and experiment with that. And this will probably give you a test bed when you read something about Kafka. You can test it by coding it yourself in here. And now the last part of today's workshop is we will look at Kubernetes as an example. Now Kubernetes is not managing data directly, like what we saw in Kafka and the erasure coding example. But Kubernetes is managing essentially Docker orchestrating execution of Docker containers. Now, how it does that is, yeah, I'm just checking if I have a better diagram. Yeah, but let's say, yeah, I will just use this diagram. So, just like Kafka had brokers, your Kubernetes cluster will have nodes on which you run a Kubernetes process called kubelet. And then on the it has a separate set of processes, one which is called as controller and one which is called as a scheduler, and it also has this component called API server, which we did not see in in Kafka like thing, right? So Kafka was directly using Zookeeper API to store metadata or to watch for changes, etc. What Kubernetes people have done is that they have abstracted out etcd from the rest of the Kubernetes components, and they exposed API, what is required for cluster management and metadata tracking, in this component called API server, which internally right now uses etcd. But obviously what it does is it decouples all the other components from etcd. And as I see, it has happened gradually. So if you see earlier versions of Kubernetes, you will see that it had many components which directly used etcd API, just like Kafka used Zookeeper. But eventually what they have done is they have wrapped etcd in the API server, and API server now exposes a lot of the APIs that etcd that other components would need. Now let's see how all these components work together to do two things. One, distribute Docker containers across a set of nodes to make sure that a single node is not overloaded, and how it detects if a container fails on some of the nodes, so that it creates it on another node to give you availability and give you fault tolerance, and we'll see how that works. But to start with, very similar to how Zookeeper stored all the required metadata and provided services for cluster coordination and management, in this case etcd plays that role, just wrapped around API server. In our implementation, we will use API server, but we will also directly use etcd API. Now what happens, similar to what with Kafka, we started with the lowermost layer, which is log, right? In Kubernetes, this kubelet program that you have, the basic facility that it provides is programmatic API to manage Docker containers. So we'll see in code how that happens, and we'll try running actual Docker containers. So now we'll open a different project. I mean, it's in the same repo. It's just that because it's not a Java project, you can't run it from the same. So in the section 05 Kubernetes, there is this folder called GoKube. You can open that as a Go project in any IDE. And this is a very miniature Kubernetes code base. What I have tried to do is, if you just see the package structure, it almost reflects the package structure of real Kubernetes code base. Looking at the time, I'm just thinking, okay, so let's anyway see how we can programmatically invoke and check status of Docker containers. So there is a test, I think called as, there is a test called as pod status test. And what this is doing, see if you can execute this. Because it will just confirm that Docker integration with your Go program is working fine. So what this is doing is just using Docker API, Docker library, Docker client library. And creating given containers and then checking their status. And the way it does that is, it's a very simple trick, but the containers that you want to be running continuously, so that when you check the status, you see that they're alive. It just runs a sleep command. For containers which you want to immediately exit, it runs a simple echo command. And for containers which you want to be failed, it just executes command exit 1. So those container processes will be marked as failed. So in that entire Kubernetes set of diagram that we saw, this is the lowest level, like the Docker client library, which is starting containers and checking container statuses. Now Kubernetes has this concept of a pod, which is group of containers which are managed together, but we will deal at the level of single container at a time. So is this test running for everyone? Is it running for everyone? Okay. So that's how basically we will manage Docker containers programmatically. Now Kubernetes has this concept of node, right? Similar to what Kafka had concept of broker. So the first thing that you need to manage in your cluster metadata is what nodes are part of your Kubernetes cluster. and we'll see how that's implemented. And because we already discussed Kafka, you will find parallels in what's happening here. So there is a class called as node registry, and what this is doing is it gets this node object, which is nothing but very similar to just name and something else. And as we discussed, Kubernetes uses etcd for storing all the cluster metadata. So almost very similar to how we stored broker metadata in Zookeeper, you see that this node metadata is stored in etcd in a very similar way. So you first create a prefixed key. So if you remember, in case of Kafka, it was /brokers/IDs. In case of Kubernetes nodes, it's /registry/nodes. And then it will create a key based on name of the node or ID of the node. By the way, this was the assignment that we had to do. So if you see in your code, this is empty. But if you see Git history, you already have the solution, because what I did was I first checked in all the code and then removed some code snippets to add assignments. So in Git history, all the code is there. And anyway, there is a solutions branch, by the way. And then it stores it as a key value in etcd. So if you see etcd storage, again very very similar to how we use Zookeeper, where we used Zookeeper client for storing that information in Zookeeper. Here we use etcd client, and if you check your node registry test, it is set up in a very similar way the way we set up Kafka tests. So it uses embedded etcd. So it starts a etcd instance within this test, so that you can use standard etcd client to talk to it over the network. So one of the advantages of these embedded alternatives to, or embedded versions of these products, is that you can write unit tests without need to set up, without the need for extra setup for these remote products. So see if this test is working for you. Very simple, create and get node information. I mean, it will fail for you, but see if you can make it pass by just replacing it with a version from Git history. And just like 5 minutes, so that you just get a chance to go through the code, just to get a feel of it. till 3:15, right? Oh, till 4 I can go on. Okay, okay. Yeah, but I won't. Cool. So if you have enough handle of what was going on there, the next thing we'll look at is if you open this replica set controller test, it adds like one more layer on top of what we had so far. So now imagine that we have a set of nodes and we want to tell whatever is orchestrating those set of nodes for containers that I want to start n number of instances of this particular container, right? So in Kubernetes there is this concept called as replica sets, and it's essentially that. So if you see this replica set controller test that we have, what it's allowing us to do is it gives an API which can tell me how many instances of a particular container I want, right? So right now I'm just telling that I want 3 instances, that's number of replicas, of this Nginx image with the name test container. Now there are 2 or 3 things that need to happen. Now again, drawing parallels to the concept of topic and the way we stored or mapped topics to nodes, or topic partitions to nodes. What we did there was we first created number of partitions for a particular topic. Then we mapped those partitions to nodes or brokers, and we stored all that information in Zookeeper. So similarly, this information needs to go in etcd, that there is a replica set such and such which expects 3 instances of a given container running on available number of nodes, right? So what I mean, the way it happens here is slightly I mean, it's divided into 2 steps. First, whenever a client tells my Kubernetes cluster that I want a replica set to be executed, first I just store this information in etcd as is. So other thing to remember or other thing to notice is that for any kind of information that goes into etcd, Kubernetes has this wrapper called as a registry. So for pod information, it has a class called pod registry. For replica set information, it has a class called replica set registry. For node information, it has a class called node registry. For Kafka and Zookeeper, it was not that clean, right? I mean, we directly use a single Zookeeper client to store all that information. So take a look at replica set registry. Is there a registry? No, there is replica set registry. Replica set registry is there, right? Yeah. So again, very similar to the node create update list kind of messages. This has replica set So when in my test I do now this test you can see what this is named is that test reconcile, and reconciliation is the functionality that this controller component implements. What that means is that when I say I want 3 instances of this test container nginx constantly running, this controller will check continuously how many instances are actually running, and if it finds that there are no instances running, it will create those many instances, and if it finds that there are more instances running, it will delete some of those instances. Now all this communication, so finally you can imagine that the actual execution or deletion of Docker container is happening in kubelet, the kubelet class that we just tested in the at the start. So now this information that these many instances need to be created on these nodes, and either they need to be created or deleted, it somehow needs to be communicated with each node, right? And for that, then there is one more component that Kubernetes architecture has. It doesn't need to be that way, but which is called as scheduler. And this responsibility of mapping container instances to nodes is handled by the scheduler process, which is an independent process that's running. So the way the functionality works is that client directly tells the cluster that I want this replica set, so this container with these many instances running. Now what controller does in its reconciliation loop, and maybe I can be very quick. But if you look at replica set controller, and maybe take 5 minutes to take a look at the code and complete that assignment, but we need to implement this reconcile method. So take maybe 5 or 10 minutes and see if you can at least think of how this reconcile method can be implemented, because that will force you to look at the code and think through some of the implementation details. I have comments there about what needs to be implemented. And as I said, there is a solutions branch as well as Git history if you want to refer to. And once you implement this particular method, this replica set controller test should pass, that test reconcile. Currently it is failing. Yeah.
Let's say we have 5 pods.
Right.
As per my calculation, I need only 3 pods.
Right.
Let's say it's scaled up too much.
So number of instances you need only 3.
3.
Yeah.
And when we set it to 3,
Yeah.
for example, if the remaining 2 pods are still serving the request,
They are still serving the request. Yeah.
and if I kill it, so it will leads to
there will be some time lag between those are actually killed on those nodes.
But will Kubernetes or the resources take care of what are the active requests in that node should be processed and then executed, or it will just mark for deletion?
No, it will probably it will mark for deletion. So the controller will just mark it for deletion. Then node will eventually figure out that there is some pod assigned to itself that's marked for deletion, and then it will kill it. But there will be a time lag between. No, go ahead.
No, no. My understanding is it will wait for the what are the requests that are being served by those particular parts to be served, and
Right.
it will kind of
Grace period of 30 seconds or so.
Yeah.
same thing happens with that's how you deployment you scale up and scale down as well.
Yeah, I mean, depending on what software is run by that container.
What is it doing?
Yeah. Because if that container itself is part of a clustered software, then it will be anyway that software's responsibility to take care of handling that. Yeah. Right.
Is it like the controller fetches the data about all the objects every time and try to bring it, look at the current state and
Yeah, there is a loop. Yeah.
wouldn't it be
I mean, it's not a loop really. So it watches for changes. So it will be notified if any change. Because what happens is it's two-way, right? So controller is, let's say, watching for changes for pods, and pods or these kubelets are continuously expected to be updating pod status. So if any change happens in pod status, you will get notification on your controller.
but when let's say I change the number of replicas from time
Okay. Yeah.
does
That time,
we send a notification to the controller, or controller has to fetch that information?
so if it's watching for that key prefix, right, slash pods, it will get notification. So it can watch for a key prefix of, say, slash replica sets, and whenever there is an update in the replica set, it will get notification. So there is a pattern called as, so whenever you need to deal with information from etcd or Zookeeper, anyway, there is a pattern called as list and watch. So you first need to get whatever is there, and then you need to watch for any further changes, and it will push the changes to it. And again, if there is a connection breakage between controller and etcd, again it needs to list and then watch.
So there are no much network calls, only during the
I mean to maintain that watch, there will be some heartbeat that it needs to send, but otherwise, I mean, it's not too chatty between I mean, it won't get all the replica set information continuously for the. So I just have isolated implementation of that list watch. There is this list watch implementation, and in Kubernetes code, if you see, there are a lot of this. Kubernetes calls it lister watcher implementations. So for every type of object, there is a list watch instance for getting information about that kind of object. So it's a notification for, similar to how Zookeeper notifies your Kafka controllers. Yeah, the way I have implemented it is like it continuously polls, but it does. Yeah, I mean it's not like this. Yes, I think what I have in here is when you start, it will just periodically it will just continuously run the. So it lists all the replica sets, and it calls reconcile on every replica set.
This might slow down
Yeah,
the reaction.
yeah. So it is not like this. It's as I said, it will be watch. So one of the to dos is to change this implementation to use that. I mean, I have that list watch thing in there, right? This pattern. I do have an example of that as well. I think no, not a very good example. Okay. So there is this exercises.md. So after, I mean, if you implement replica set reconciliation, the next thing is implementing the scheduler. And once that's done, there is this end-to-end test, very similar to that producer consumer test that we had. And what this does is it sets up a test cluster with kubelet processes, again all happening embedded, and it starts a controller and a scheduler. Starts 3 kubelets for now, and then it just executes this create replica set, where it says you execute nginx and 3 instances of it, and then it waits for pods actually getting created, and then kubelets picking up that the pod is assigned to it, and the containers actually running. So what you should expect after your scheduler implementation is done, and if you run this test, you will actually see 3 nginx containers running, because there are the replica set said 3 containers, and we can experiment by changing this replica set definition. So maybe if I say 5 containers, so you can see that because now there were only 3 nodes, it assigned 3 pods to one node and then 2 pods to the remaining node. But it did create 5 containers when we changed the replica set definition. So everything is right now on local machine. The number of nodes is decided by number of kubelet instances that I start. So in real life, each node will have a single kubelet representing, because kubelet instance represents a physical node. In our tests right now, we are just starting n number of kubelet, so everything is happening on the same machine right now. Cool. So we are at 3:15, but take your time to go through complete that reconcile and schedule and draw parallels between the partitions, how they were mapped to the brokers, and how the pods are getting mapped to nodes.
How are you? So this your implementation doesn't make use of that branch or desktop or any of the context, right? Is it making use of it?
I mean, it's making use of Docker runtime.
Okay, if I just have Docker, is that good enough for these tests, or do I need to have that branch or desktop?
Yeah, you probably don't.
Because like you are kind of essentially running all of that.
Running all of that
node
as a
in
yeah.
different node.
Yeah.
I mean, your implementation is providing the runtime.
Yeah.
So it's like Docker is good enough, not the
Yeah.
branch.
Yeah. Ah, you are good. Yeah. Put that in the where is the? You send me the QR. Okay. Yeah, yeah. How do I create a QR code for this? QR code for this link, is it? How do you do that? Can you send me? Okay. By the way, do share your feedback on this. Or I can send it in WhatsApp as well. You can just send it to the WhatsApp. Yeah. Ankit, I will share the PPT as well. Yeah, and if anyone has any questions about reconciliation and scheduling, we can discuss. I mean, this was very like a fast track introduction to. But what I was hoping to have is like a miniature code bases next to each other, like this Minayo and Kafka and Kubernetes, so that if you want to explore things further, you can do that. Yeah, we can close the live stream. No.